Hey, here we are at lesson 21. So we're going to talk about the central limit theorem. So we're going to talk about when we are taking those samples repeatedly, especially when the sample size is big, what we can expect to happen to that sampling distribution of x bar. Okay, so where we're going to start out here, we are going to want to know the mean for a population. This is often the case. We want to know, hey, what is the average, age of people in the U.S. that test positive for the coronavirus. Hint, that's a throw to the data analysis. You might want to know some average value for a population. So you're going to go ahead, you're going to take a random sample, calculate the sample mean for that sample. And then you're going to repeat. So take another random sample, get another sample mean, and so on. A lot more than just 3 times, but we're showing it 3 times to illustrate that we're repeatedly doing this. And you can go ahead, you can plot all the unique sample means that you get from collecting all the unique samples of whatever size you decide ahead of time from the population. And you might notice it has this great shape to it, right? It's centered right where we want to be able to estimate the population mean. And we can describe its standard deviation. So, on average, the expected value for x bar is going to be, well, mu of x bar, which is equal to mu of x. So it's equal to the mean of the variable we're interested in. The standard deviation of x bar, it gets this notation like standard deviation of x bar. It's equal to the standard deviation of the population divided by the square root of your sample size. So in this sense, it's very important how big or small your sample is. The smaller your sample, the bigger the spread. The bigger the sample, the smaller the spread, that kind of idea. And thanks to central limit theorem, not only does it tell us where it's centered and about its spread, it also tells us about its shape. So you might have seen, hey, this familiar bell-shaped curve. If n is sufficiently large, and we'll talk about what the heck we mean there, the central limit theorem kicks in. So it says, okay, well, the distribution of all the sample means, they're going to be roughly normally shaped with a mean or a center of mu and a standard deviation of sigma of x over root n. So this is a really, really useful property that we use a lot. It is absolutely important to ascertain whether or not our sample size is big enough. So yeah, we're going to talk about what we mean by sufficiently large. So it must be sufficiently large in order to kick in. In general, so when we are looking at means, we want to have sample sizes of at least 30. That's our happy place. Unless it's Bernoulli data. So later on, I want to say 2 or 3 weeks from now, we're going to look at proportions, categorical data. That's what this Bernoulli data is. That has its own demands for what is big enough. So if you're looking at means, samples of 30 or more are big enough for us. So just to show you, when we have a quantitative variable and the population is normally distributed, as long as you take a sample of at least 1, which honestly I don't think you could take a smaller one, your sampling distribution is going to be nice and normal. If you have a population that's symmetric, like this fairly uniform shaped distribution, but it's not normal, so it's not this, it's symmetric with like a single peak kind of shape, make sure you take samples of at least 12. And if you take samples of at least 12, the sampling distribution's going to still come out pretty normally shaped. If you have your population data are skewed, especially like extremely skewed or you have extreme outliers, a lot of times incomes are one of those. Almost always you have some fat cats up top making big bucks and most people are down here. You're going to want to take a bigger sample in order to account for this. You're going to need to take a sample of at least 30. Sometimes it needs to be more, but usually we're going to use at least 30. With a grain of salt, I want to add, we're saying that 30 is close enough to infinity to work. And it is for our purposes. But just keep in mind, the last time you thought of the number 30 and you thought of that as like infinity, because I'm not going to check my bank account anytime soon, see $30 and go, yes, I can quit. So just grain of salt, want to throw that out there. In some senses, it's not close to infinity, but it's close enough for sample sizes and stats. And then the last one, we're going to review this definitely in a couple of weeks. But if you have Bernoulli data, so usually this means categorical to categories, you're going to need to have a specific, according to whatever P is, minimum sample size. And we'll go into that. So in general, these scenarios, if you are taking a quantitative variable, sample sizes of at least 30 make us happy. Smaller ones make us nervous. We start trying to check out, hey, is it symmetric or not? When we are lucky enough to know the population is normally distributed, it's easy. Any sample size is good. Oops. So some examples here. So if I have a normal population, there's no sample size condition. That means as long as I take pretty much any sample size, it's going to be good enough. My sampling distribution of X bar is going to be normally distributed. So here, I went ahead, my population here is the standard normal distribution, right? So it's a normal distribution with a mean of 0, a standard deviation of 1. If you take samples of 3, all the unique samples of 3, and you average them, that looks pretty normal. If I up it to 30, it looks pretty normal, but narrower. If I take 100, it's normal, but even narrower, right? Because they're all centered at 0, where the population is centered. Then in contrast, when I have a population that is not normally distributed, you need to have a bigger sample size. Usually our rule of thumb, at least 30. So if this is my population here, it's very skewed. Not only that, it's right skewed, because the tail is on the right. When I take samples of only 3 and take all the sample means, that's not quite normal. No, the sample size wasn't big enough for the central limit theorem to fully kick in. If I'm taking 30, that looks a lot better. That looks a lot more normal. And by the time I'm taking 100, yes, that looks pretty normal. So it doesn't matter that the population was very skewed. If I'm taking samples of 100, the sampling distribution of X bar will look pretty normal. So finding probabilities and proportions. So for week 4, we're on week 4, right? We are going to be looking at Z methods, also known as Z procedures. So if you see them, we're using those interchangeably. So if you have a value for X bar, a sample mean that was observed in a sample, you can convert it into a Z-score, and you can use that Z table, or R, to go ahead and calculate your probability. So here's what's observed or speculated here. This is the mean of my sampling distribution, which is also equal to the mean of the population divided by the standard deviation of X bar. So I went ahead and I just plugged in. Definitely keep tabs on all this. This is just mean of the whole population, standard deviation of the whole population divided by root n. So these two, they're equal to each other. If calculating it one way versus the other makes you more comfortable, by all means, but they are equivalent. So we're going to go through this example here. We have a pool cleaning company. I'm not sure they would be super busy right now. I don't know. I mean, I feel like a lot of public pools are definitely closed with the whole remote everything. But I guess people have personal pools. I don't know. Seems kind of iffy. But so they go ahead, they record the time it takes for their employees to clean all of the pools for all of their customers. And they notice, looking at times, this is hours to clean a pool, is super skewed, right? Like a lot of the cleaning times are very, very low, and very few of the cleaning times are very high. So, and that's probably not too surprising. I mean, I imagine they're not all the same size pool, but it's hard to tell. This distribution is strongly skewed, and it's skewed right because the tail is on the right, and it has a mean. So this is telling me this distribution, this is talking about population. So it has a mean of 1 hour, so mu is 1 hour, and a standard deviation of 1 hour. And suppose I take 50 pool cleaning times. So this is my have a sample of 50. And the sample mean, I guess I could stick that here, is 0.9 hours. And we will use that on a later slide, not particularly on this one. So my random variable that I'm collecting here, it's time to clean pools. The average of all the time to clean pools is 1 hour. The standard deviation of all times to clean pools is 1 hour. Draw the distribution for the sample mean. So n big enough for the central limit theorem to kick in. So remember, it's skewed. If it's skewed, we want to have a sample of at least 30. I have a sample of 50. It's going to be good. So n is 50. Yes, yes, it will kick in. So mu of x, so mu of x bar is equal to mu of x, which is equal to 1 hour. So it's going to be centered at, 1 hour. I'm going to write hours here because I don't want to write them after every single one. So this is mu. I like to draw the line down the middle. You don't have to draw this specific line here. It just helps me visualize where the mean is. So I know that x bar is going to be approximately normal. I guess you put a dot over it. This is saying it follows a normal distribution. The dot means approximately. With a mean of mu and a standard deviation of sigma of x over root n. So we can go ahead and calculate this. It's normally distributed with a mean of 1 and a standard deviation of 1 divided by the square root of 50. Did I go ahead and write this? That's about 0.14 hours. Technically, both of these are still in hours. So if I want to draw my distribution, you will note, like a lot of the time we say, hey, with mu plus or minus 1 standard deviation, mu plus or minus 2, mu plus or minus 3 standard deviations. What we mean is we want you to draw this curve and fill out the mean. Mu should be the first thing you fill out, but fill out to 3 tick marks in either direction. That's all we want. We want you to fill in these 3 tick marks. So 1 plus that 0.14, I'm estimating here a little bit, plus 1.4 plus 1.444. You could keep going, but the area out there gets really, really tiny. Subtracting, I'm less confident. 1 minus 0.14, 0.86 minus 0.14. 0.58. So this is what we mean by draw the distribution. We want you to show this roughly normal shape, and we want you to give us the values that go with the center, and then 3 tick marks to the left and 3 tick marks to the right. That's what we want. So to answer another question here, because we did hint here, the mean of 0.9 hours. So we want to now calculate the probability of obtaining a sample mean of 0.9 hours or less when we take a sample of 50. So we took 50 observations, pool cleaning times, and we had a X bar of 0.9 hours. We want to know what's the probability that if I took a random sample of 50 from that population, what's the probability that I would have seen a sample mean of 0.9 hours or less. So here, I'm just going to kind of redoodle this. So centered at 1, and I'm going to write 0.14 here. So 1, 1.14, 1.28. I'm going to go this direction here. 0.86. I'm not going to go all the way out. So what it's asking is if I had 0.9 hours or less, what is this probability? So what we're going to do is we're going to convert it to a z-statistic and use the z-table to get that probability. So here, I'm going to go ahead and calculate z is equal to x bar minus mu of x bar minus sigma of x bar, which is, so 0.9 is what we observed, minus the average of the population over the spread of the sampling distribution here. So that 0.14. By all means, you're welcome to put 1 divided by the square root of 50 as well. That will be the same. So here, I get a negative value because what we observed was less than the average. So I get negative 0.71, roughly. With z-statistics, we almost never round them more than 2 places past the decimal if we plan to use a z-table, because the z-table only goes to 2 places past the decimal in general. So if I want to know the probability that I take a sample of 50 and see 0.9 hours or less, that's going to be equal to the probability that on the z distribution, that standard normal distribution, that I see less than or equal to negative 0.71. Note the signs here should be the same. So here, if I went here, negative 0.71, what we're saying is the areas here, this area, and this area, those 2 probabilities, they'll be the same. So while I don't have a table to figure out this probability, I do have a table for the normal 0, 1, so I can find this probability using that. Once again, you're totally welcome to use R as well. So I want to find the probability that z is less than 0.71 or negative 0.71. So here, and I'm interested in this shaded probability. I am really a fan of drawing out, like, do I want the less than, or greater than, because it helps me know if I should take this area or this area, that kind of idea. So I can break this up to negative 0.7 and to 0.01, 0.01, negative 0.7. Obviously, this slide is very doctored. This table is actually much bigger than this. So 0.235. Oops, I'm looking at the wrong one. 89. So what this is saying is, 89. If I were to randomly sample 50 pool cleaning times from this company, from all of their pool cleaning times, the probability that I'd take a sample of 50 and get an average pool cleaning time of 0.9 hours or less, that happens about 23.8% of the time, given the distribution of the population. So, somewhat often, not quite a quarter of the time. And so here's another one. We have a buzzer on a board game. It's set to go off anywhere between 20 and 120 seconds. You might notice it's kind of uniformly shaped. So the population of all buzzer times have an average time of 70 seconds. So X is buzzer times. We're collecting buzzer times. The average of all the buzzer times is 70 seconds. and the standard deviation. So a lot of the times the giveaway, like we may not use the word population, but if we do, you can assume that's the population. The word all has a tendency to be a giveaway that we're talking about a population. So the standard deviation of all is 29 seconds. That's a prime number, is not going to divide nicely. And we go ahead and we're going to take 15 buzzer times. So we're going to consider these 15 buzzer times as a random sample, and the sample mean is going to be a random variable. So things to consider: this is a very symmetric distribution. In fact, I would argue it looks like a uniform distribution. So if I fold it in half, it would be roughly the same on each side. So I need, n big enough for central limit theorem to kick in. If I take a sample of 15, yes. So n equals 15, yes. Because population symmetric. So because the population is symmetric, a sample of 15 is going to be big enough. So we know that the sampling distribution of x bar is going to be roughly normal with a mean of mu and standard deviation of sigma of x over root n. So we can say, okay, well, x bar is going to be roughly normal with a mean of 70 seconds. The standard deviation of 29 over root 15. I'm going to take a peek here. That's not doing my head kind of math. I am going to round here just for the sake of, because I want to label these tick marks. 7.49. These are both in seconds. So here I'm going to write seconds. So this right here, it tells me it's going to be normally shaped, so it's going to have that bell shape with a mean of 70, so that's where it's going to be centered. So that's what I have here. And a standard deviation of about 7.49 seconds. So that means each one of these tick marks is going to be about 7.49 seconds apart. So this will be 77.49, 84.98, 92.47. I tend to do the addition first because I am so much shakier about the subtraction. 1, 55.02, and 47.53. So anytime that we ask you to define the distribution and draw it, we're looking for you to draw something roughly bell-shaped. We want to see where the center is, and we want you to label 3 tick marks to either end. And here, I went ahead and specified, okay, well, it's roughly, normally distributed, and I gave the mean and the standard deviation. So now that we have that, we can answer questions. So, for instance, I suppose I take a sample of 15 buzzer times from this buzzer game, and I want to know the probability that I take 15 buzzer times and the average is 80 seconds or more when my sample size is 15. So n is 15. 80 seconds or more is what I'm interested in. This is x bar. Actually 80 seconds. So mu is 70 seconds. And this is that, about 7.49 seconds. So this is equal to that sigma of x over root n, which was 29 divided by the square root of 15. So here, my x bar is about 70 and 7.49, 70, 77.49, oh, that was actually sort of okay, and then 84.98. So somewhere in between here, I want to know 80 or higher. So that's the probability that I'm interested in here. So I know it's somewhere between 1 and 2 standard deviations above the mean, but we can calculate our z-stat for that. So x bar minus u of x bar over the standard deviation of x bar. So 80 is the value we're interested in, which is higher than the mean, so I should get a positive z statistic. The minus 70 is the average over the spread of the sampling distribution. So I'm going to put the 7.49. Note that I did round here. So if you're doing something like WebAssign, it tends to prefer you not round until the very end. This is me rounding. So just be cautious there. So I get positive 1.34. So once again, I only rounded it 2 places past the decimal for a z statistic. In particular, if you're going to use a z table, it usually only makes sense to go to 2 places. So I said it was between 1 and 2 because I knew it was higher than 77.49 but lower than 84.98. So 1.34 standard deviations above the average here. So I can use a z table to find this area, and it's the same as that. So probability x bar is greater than or equal to 80. That's the same as probability that z is greater than or equal to positive 1.34. So, well, 1.34. Technically, these are the same. So, remember, if this is 1.34 here, it's positive. I want this yellow area, not this blue area, because I want greater than. So I'm going to have to do a 1 minus bit. So I can break this up into 1.3, 0.04, 1.3, and 0.04. So this is 0.9099, which means the yellow area is going to be 1 minus that. So it should be what, about 9% or so. 901. So 1 minus 0.9099, which is equal to 0.0901. So .0901. So what this is getting at is if I were to take a random sample of 15 buzzer times from this population, the probability that I would get a sample mean of 80 seconds or more from a sample of 15, that happens about 9% of the time, a little over 9%. So I can absolutely, now that I know, hey, essential limit theorem is going to kick in, I know that it follows a normal distribution, so I can use z-scores to find probabilities that I'm interested in. So coming up next, we're going to go ahead and use that information in confidence intervals to help estimate values of parameters. So we're going to start out trying to estimate what the mean of a population is and work from there.